In section 2.2, we're going to talk about a limit. And in order for us to find the instantaneous rate of change from our previous section, without using a table, we need to first talk about limits. So we're going to look at first the limit of a function, but this is just a preliminary definition. We're going to look at a formal definition of a limit in a later section. This is just so that we can get an idea of what a limit actually is. So if you were to read this preliminary definition, it's a bit confusing. So suppose the function f is defined for all x near a except possibly at a if f of x is close to L, as close to L as we like, for all x sufficiently close but not equal to a, we write. And that's where I'm going to stop, because that's just a bunch of blah, 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 blah. So what all that means, and then we'll finish this in just a second, is easier to understand if you look at this graph. So let's go ahead and consider this function f of x, which is the square root of x. So here I have my function f of x, and that's the square root of x. Well, in this case, we want to look at what happens as x approaches 4. So since x is approaching 4, that would be the a value in that definition. So what this says is, as we get closer and closer to a, or in this case 4, what is happening to f of x? F of x are our y values. So as the x values get closer to 4, what are our y values getting closer and closer to? Okay? Well, that depends. If our x values are getting closer and closer and closer to 4, from the right-hand side, then on our graph, we can see the y values are getting closer and closer and closer to 2. And if we approach 4 from the left-hand side, and we get closer and closer and closer to 4 from the left-hand side, then we're looking at the left-hand portion of our graph. Those y values get closer and closer and closer also to 2. So this y value of 2, that's L. That's our limit. So the limit is a y value. All this stuff means is that as we get closer and closer to our a value, which is an x value, so as our x's get closer and closer to a, what are our y values getting closer and closer to? So if the y values are getting closer and closer and closer to some number, and in this case, coming in from the left or the right, our y values are getting closer and closer to 2, then 2 is L, our limit. And we write the limit as x approaches 4, that's our a value, of our function f of x, which in this case f of x is the square root of x. That's going to be equal to our limit L. Our limit L is 2. Okay, so again, as your x values approach some a value, what are your y values approaching? If they approach this number L, then that's the limit. So we can find the limit by looking at a graph, or we can find a limit by making a table, similar to the table that we made in the previous section. So this would be figuring out a limit numerically. So remember, we can come in from the left or the right. So if I were to come in from the left-hand side, these are going to be numbers that are smaller than 4, like 3.9, 3.99, 3.999, and so on. So as these x values approach 4 from the left, what are the y values approaching, which would be our f of x? So the f of x, or our y values, are getting closer and closer and closer and closer to, it looks like 2. As we approach 4 from the right-hand side, so these are numbers that are a little bit larger than 4, like 4.1, 4.01, 4.001, 4.0001. What are our y values approaching? So you can see these y values are getting closer and closer and closer to 2. So as we come in from the left, or as we come in from the right, our y values are approaching 2. So again, we say the limit as x approaches 4 of the function square root of x, that's going to be equal to 2. But notice that the y value has to be the same coming in from both the left and the right. So sometimes we don't come in from both sides. Sometimes we just come in from one side. In this definition of one-sided limits, we're going to look at right-hand limit and left-hand limit. So a right-hand limit says, suppose f is defined for all x near a with x greater than a, blah, 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 blah. Okay, a right-hand limit just means you're coming in from the right. The way that we denote that we're coming in from the right is, instead of our x value approaching a, our x value is going to be approaching a with a plus. So that plus means we're coming in from the right. Plus means we're looking at a values, we're looking at values that are larger than a. So they're plus a, or coming in from the right. The left-handed limit has a minus, and that just means we're coming in from the left. So the minus means coming in from the left. The minus means we're coming in with numbers that are less than a. So why would we need to do left or right-handed limits? That we're going to look at in our next slide. We're going to go back to that function, square root of x, that we had before in example 1. And we're going to look at one-sided limits first. So in example A, we're looking at the limit as x approaches 0 from the right. Okay? So we're getting closer and closer to 0, but we're coming in from the right-hand side. So as x approaches 0 from the right, the graph, the y values, are getting closer and closer to 0. So this is equal to 0. In part B, we're looking at the limit as x approaches 0 from the left. The problem is, as we come in from the left and our x values get closer and closer to 0 from the left, the problem is we have no graph. There's nothing here. So since there is no graph, we cannot come in from the left. So the limit doesn't exist there. Our y values don't exist, so we can't be approaching anything. So we can say the limit does not exist. And a shortened term that we often use in calculus is DNE, for does not exist. Let's look at part C. So part C, our x values are approaching 0. Notice there's no plus, there's no minus. That means we're coming in from both sides. Okay? However, we cannot come in from both sides. So this limit does not exist. In order for the limit to exist, when you come in from both sides have to approach the same value L. And in this case, they don't. The limit coming in from the left and the limit coming in from the right are different. Let's look at another example. Let's look at example 2 with a different function. Okay? So here's my function, and here's the graph of my function. We're going to find the limits and write DNE if the limit does not exist. Part A, we're supposed to find the limit as x approaches 0 from the right. So we're here at 0, and we're coming in from the right. So as we come in from the right, on our graph, we're getting closer and closer to the y value of 6. So this is going to be equal to 6. Okay. In part B, we're looking for the limit as x gets closer and closer to 2, coming in from the left. So as we're coming in from the left and we're getting closer and closer to 2, our graph is getting closer and closer and closer and closer to a y value of, it looks like the y value is 2. So this would be equal to 2. Now in part C, we're approaching 2 from the right. So as our x values get closer and closer to 2 from the right, our y values are getting closer and closer and closer to, it looks like the y values are getting closer and closer to 1. So that would be equal to 1. In part D, we're looking at the limit as x approaches 2, not from the left and right, from both sides. So notice that as we come in from the left, the limit is 2. As we come in from the right, the limit is 1. Since those limits differ, since they're different, the limit as x approaches 2 does not exist. So that brings us to this theorem 2.1. In theorem 2.1, it says that assume f is defined for all x near a except possibly at a. So this is the important part. The limit as x approaches a of our function is equal to the limit L if and only if as we come in from the right and the left we approach the same number L. So again, the limit exists if coming in from the left and the right we get the same number. And here's our next slide. In example 3, this is a little bit different. I'm actually not given a function. What I'm given is I'm given some properties, and I'm supposed to sketch a function that fits those properties. So there's going to be infinitely many functions that can fit the 4 criteria here. I'm just going to do one example. So if we look at f of negative 2 equal to 2, Then at -2, we have this point -2, 2. So that's done. F of 3 equal to -2 means when x is 3, y is -2, and we have another point. So we also have this criteria that as we approach 3 from the right, our function is going to approach 4, a positive 4. So what I'm going to do is I'm going to put an open circle there. Because remember, the limit says it approaches, but it doesn't have to reach it. It just has to get very close. And I can't put a solid dot there because I already have a solid dot at -2. If they were both solid, this would not be a function because it wouldn't pass the vertical line test. So I'm going to look at the other limit. The limit as x approaches 3 from the left, it's going to be a positive 2. So I'm going to put an open circle there. So coming in from the left, I have to get closer and closer and closer to positive 2. Coming in from the right, I have to get closer and closer and closer to 4. And that's a function that fits all of these criteria. Right? As I come in from the right, it's approaching 4. As I come in from the left, I'm approaching 2. Of course, it's not unique. There would be infinitely many functions that fit this criteria. And in fact, I can keep going in this direction, and I have another function. But I don't have to have these horizontal lines. I can have curves. I can do whatever I want, as long as I meet those 4 criteria. Let's look at another example when one where we're looking at a graph and finding limits. In example 4, we have this piecewise graph. In part A, we're trying to find the limit as we approach 0 from the right. So if we're coming in to 0 from the right, then we're just using this small piece of graph here. Notice the y values are getting closer and closer to 0. And as we approach 2 from the left, so I'm approaching 2, I'm coming in from the left. Then the part of graph that I'm using is this one little horizontal piece here. So as I get closer and closer to 2, my y values are getting closer and closer to 3. All right. So let's look at part C. This time we're going to be approaching 2 from the right. So as we approach 2 from the right, we're coming down on this graph, and our y values are approaching 2. So when we look at part D, the limit as x approaches 2, since the left and the right limits are different, that would be a does not exist. So it only exists if they're the same as in the very first example we did. That's it for this section. Again, later sections we're going to be able to compute limits by not just looking at graphs or just making tables. We're going to be computing them in a more efficient way.